You are unable to touch this screen with your fingers. You are even unable to touch your own fingers. In fact, no one has ever truly managed to touch anything. Sit down, make yourself comfortable. Now ask yourself, what am I sitting on? The answer to this question, which seems as simple as it is absurd, is quite astonishing. Suppose you're sitting on a wooden chair. It's easy to think you're sitting directly on it. Except that in reality, it would be just as accurate to say that your backside is somehow floating above the chair, trying to get close to it. Why? We'll need to look at what, on the atomic scale, makes up all matter, all objects, backsides, chairs, sofas, you and me, and even fingers. Namely, atoms. The first thing that stands out when you look at atoms is that the space between their components is phenomenal. In fact, if you enlarge the nucleus of an atom to about the size of a millimeter, then, proportionally speaking, you end up with electrons swirling nearly 100 meters away in the form of strange and vast electronic clouds. So, if we think of atoms in terms of the volume occupied by the particles they contain, they are almost entirely made up of empty space. And in doing so, from this point of view, you are essentially sitting on almost nothing of the almost nothing that you are not passing through or touching. In fact, as strange as it may seem, when you stub your toe on a corner, the only thing you encounter besides pain is resistance related to the sheer power of an extraordinary force, the electromagnetic force. Yet you agree it seems like they're touching. Except that if we do have this visual impression, it's because our eyes, which struggle to distinguish details smaller than 1/10 of a millimeter, are playing tricks on us. In reality, the atoms in your fingers, just like in anything else, only get as close as a few billionths of a meter at most, which means you've never actually touched. Okay, that sentence is really weird, so why can't we touch anything? The explanation for why lies in the electromagnetic force. In the realm of the very small, that force is by far the one that reigns supreme. Here, gravity is kind of not even invited, because at atomic scales, the electromagnetic force increases as the distance between two charged particles decreases. It's about a billion times more powerful than the force of gravity. And it's this force that tells charged particles how they should behave. That's why, the closer you try to bring two atoms together, the more the repulsion between the charges of the electron clouds opposes this movement. It's like two powerful magnets fiercely defending their position, their territory. Let's take a closer look at what's happening, roughly speaking. Each atom contains a positively charged nucleus at its center, surrounded by electrons that form diffuse electron clouds. These clouds are negatively charged and can take on amazing shapes. In fact, it's the position and number of these clouds forming around the nucleus, a complex layered electronic structure, that determines whether or not atoms can bond. To put it simply, when these atoms are not willing to give up or accept new electrons, and when the electron clouds get close enough, they start to deform. So, the atoms we try to bring into contact always shift slightly from a spherical shape to take on an egg-like form. And the new distribution of the electron clouds surrounding the nuclei has a strange consequence. It creates a very small difference in charge between the two sides, thus creating a kind of tiny polarized dipole, a tiny magnet, if you will. And it's the sum of these charges facing each other that is distributed across the billions and billions of atoms, making up your entire butt and its support, which together form a gigantic repulsor. And so, because of these repulsions that occur between atoms, like a levitating magnet, so your butt is, in a way, floating at a ridiculously small distance from the atoms that make up the surface of your seat. More precisely, this applies if you're sitting completely naked. If that's not the case, please adjust the parameters of the experiment, and obviously this applies to everything and anything. At the atomic level, your feet don't actually touch your socks, whose outer atoms aren't really in contact with those of your shoes, whose soles will never, strictly speaking, touch the ground. In short, no matter how hard you press, you won't actually be able to make real contact. In fact, even if you drop the Bourgeois on one of your fingers, all you would do is deform and break down large molecular or cellular structures along their lines of strength and weakness. But at no point would the atoms in your now crushed fingers and those at the base of the Bourgeois qualifat actually come into contact, in the strict sense. Once again, in the realm of the infinitely small, nothing ever truly touches, strictly speaking. It's worth noting that it's also the sum of all these combined resistances that means, even though atoms are made up almost entirely of emptiness, you don't see your butt go through the objects you sit on, which, let's be honest, is actually pretty good news. Alright, all of this is nice, but the exaggerated example I gave earlier was about two isolated atoms. But, as you may have noticed in nature, atoms are only rarely alone. Generally, they love to bond, to gather in groups, sometimes huge ones, by forming molecules. So, how can atoms bond, form molecules and objects if they can't touch each other? That's a very good question. Thank you for asking me. Actually, we can see molecules as large gatherings where atoms sort of stick together. They link up and associate without touching each other by sharing some of their electrons. It's like forming bonds, a kind of sticky electronic clouds. And the strength of these bonds varies greatly from one association of atoms to another in different molecules. Let's take relatively solid objects like you or a chair. You are both the same in that regard. Made up of long carbon-based molecules within which many atoms are strongly bonded together. This is the main reason why, when you put two solid objects in contact, they don't fuse together at the atomic level. Their bonds are very strong, creating barriers that block anything from passing through. They simply don't stick. If the atoms in your butt and a chair refuse so strongly to mix with the outside world, it's because all the available positions to accommodate electron clouds are already filled. There's no more room to form new bonds. Obviously, this observation only applies under normal conditions, but when you move away from them, you can break the locks of these atomic chains. For example, if you immerse objects that refuse to fuse in an acid bath or heat them strongly, their molecular cohesion won't last long. And in the end, you'll get a completely different atomic arrangement at the nanometric scale. These electronic influence wars that atoms wage through their clouds happen at a very short distance, but at a distance nonetheless. It may seem strange, but when a force acts between two objects, they don't necessarily need to be in contact. Take a parachutist, for example. He is pulled by Earth's gravity without needing to touch its surface, a surface he actually never really touches. The fact that our atoms are generally unwilling to give up or accept electron clouds is good news. Otherwise, our lives would be a nightmare because we'd constantly stick to everything. Let's note that there's a gentler way to stick to objects without having to form atomic bonds that are hard to break. For that, you can simply take advantage of the polarization properties of atoms that we talked about at the beginning. Because counterintuitively, this very slight difference in charge on either side of the atoms allows, in certain specific cases, to generate, at very small scales, attractive forces rather than repulsive ones. This technique is notably used brilliantly by a large number of animals. The arrangement of the electron clouds surrounding the molecules that make up their feet allows them to adhere, to stick to the surfaces on which they move without any atomic bond being formed. But if you're neither a gecko nor a spider walking on the ceiling, you can also simply stick something by rubbing a balloon on a piece of fabric. That way, you'll pull a large number of electrons from the fabric, giving it a temporary magical ability, the ability to polarize the atoms of anything you like. If we set aside these somewhat special cases, whenever atoms stick together, it's always because they have spaces to share in their electron shells, available spots for clouds. And when atoms with such configurations come close together, they don't fiercely defend their territory, but instead bond to form molecules whose properties are extremely different from those of the individual elements that make them up. To convince you that by mixing two elements that seem completely opposed, you can obtain a third with totally different properties, let's take a concrete example. Pure sodium is a highly unstable metal that, when it comes into contact with water, has an unfortunate tendency to explode in your face. Chlorine, to put it politely, isn't exactly friendly. If you inhale this terribly toxic gas, it will combine with the moist membranes in your lungs to form delightful acidic substances that will attack your tissues, putting you through agony. Now, if you put these two elements together in a closed container, well, after a few minutes, you get an impressive reaction and sodium chloride, also known as table salt. Well, you could also end up with one foot in the grave or in the hospital if you haven't taken all the necessary precautions to handle these elements. Because this chemical reaction is a highly exothermic reaction. If this chemical reaction is so impressive, it's because both sodium and chlorine have electron shells that are not completely filled. And they fit together perfectly, releasing large amounts of heat and radiation in the process. So, why is it that when we ingest a bit of salt, the sodium it contains doesn't make us fizz, unfortunately, by reacting with the water in our bodies? Well, that's simply because when sodium dissolves, it ends up with one less electron on its outer electron shell. A tiny electron which, just like in the case of dissolved chlorine, here makes all the difference between a deadly behavior or one that's beneficial in small amounts for the body. And personally, I find that a bit touching. That according to affinities and hostilities, all these incredibly varied chemical reactions allow for the existence of an almost infinite number of objects. Let's note that the rule according to which atoms don't like to stay alone obviously has a few counterexamples. Thus, the so-called noble gases, such as helium, neon, argon, krypton, or xenon, I love these names, they are exceptions. For them, the electron shells are saturated, completely full. And their particular arrangement makes them seem like they're surrounded by an armored shell that prevents them from bonding with other elements, so they remain eternally solitary. In short, if you're frustrated by the idea that you'll never be closer to your loved one than a few nanometers. Because when we kiss, the repulsive forces of the outer electron shells of the atoms that make up the molecules of our respective lips tactfully prevent any contact. Don't worry, just because you're not touching doesn't mean there's no attraction. And besides, there are radical solutions in nature to bring atoms close enough to actually make them touch. They invariably involve plunging matter into hellish energetic conditions. One of the solutions is to accelerate a few atoms to speeds approaching the speed of light and then make them collide. Unfortunately, these events usually involve only a few atoms at a time. Extremely rare on Earth, they occur near radioactive elements in very small volumes at the center of our particle accelerators, or in the upper atmosphere when highly energetic cosmic rays reach us from space. But if you think bigger, I strongly suggest you look toward the hearts of stars. Places where atoms, heated to tremendous temperatures, have incredibly intense interactions with each other, to the point where electronic repulsions can be overcome. And these atoms occasionally end up almost embracing, fusing together. In fact, it's the transformation of part of this matter into pure energy that allows stars to shine. In other words, our sun, like all the other stars in our universe, shines because at their core, matter manages to touch itself. And if what you're looking for is the most contact possible all at once, it's better to turn directly to stars with more than 8 solar masses. Because when these stars reach the end of their lives, victims of their own weight, they collapse in on themselves, dragging some of their matter toward the center at tremendous speeds. And in this infernal blaze, the overheated electrons and protons are so compressed that they end up crashing into each other. They fuse to form neutrons, while releasing an absolutely colossal amount of energy in the process. Depending on the mass of the collapsed giant star, the descent into hell of the compressed matter at the center will continue until it forms a black hole, or it will stop at the state of a neutron star. A celestial body so compact that the volume of a matchbox filled with its matter. One of these stars contains as much mass as a cube of rock 800 meters on each side. On our planet, all things considered, maybe it's a good thing for our physical integrity that matter doesn't come into contact so easily. The fact that touching something soft, rough, or sticky is, on a large scale, the sum of resistance, of electronic clouds that the sensory receptors in your skin interpret and convert into electrical signals that travel along your nerves before being translated into sensations by your brain. That takes absolutely nothing away from the spice of life. Sorry, from its sodium chloride. Maybe it even adds a little something extra, a touch of craziness. In any case, I hope I managed to give you a little taste of it. The fact that, in the infinitely small, the concept of contact always ends up shattering.